So in these groups of problems, we're asked to evaluate the limits, and it mentions that we do need to show work. Numbers alone without justification will receive no credit. So remember, the whole point of free response problems on the test is you're showing me the reasoning that we've learned throughout our calculus course. So as we look for this first limit, we know that you could look at the limit of the top and divide it by the limit of the bottom, provided the limit exists. But notice, if you try to evaluate 4 into this expression, you would get 4 squared minus 24 plus 8, which would still give us a 0 in the denominator. So we can't just use the quotient law for limits to evaluate this, but since this is a polynomial, we might hope that if we factor, we could simplify the expression and get rid of the term that's causing the 0 on the bottom. Okay, so x, since these are positive and this is negative, the only way to get positive after multiplying is positive, positive, negative, negative. Since that's negative, we have this being a negative. Okay. And I think if we do 2 and 4, these will multiply to give us positive 8, but add together to give us a negative 6x. So that's our factor. And then through limits, within limits, it's true that repeated factors above and below the fraction cancel, only within the limit, so that this limit simplifies. And notice I keep writing the limit expression until I'm actually ready to take the limit. So now I'm ready to take the limit, and I could either go through my limit laws, or I could say that this is a continuous function on its domain because it's a rational function whose denominator is not 0. And if you use that reasoning, just write it out briefly. So this is a rational function, polynomial over polynomial. This means it's continuous, which means we can use the substitution theorem. So we get that the limit as x goes to 4 of 1 over x minus 2 is the same as the value of the function at that point, which would be 1/2. Great. So looking at our next example, here we look at the expression, and if we would plug in our point, we know to the top that would give us 2. We need to see what would happen at the bottom, because if it's not 0, then we can use the idea that we know the limit of the top and the limit of the bottom are both polynomials, so we can substitute in. So off to the side, I'm just going to briefly sketch 6 squared minus 36 plus 8. That's just going to give you a positive 8, which is not equal to 0. So that's enough of an indication that we can indeed split this limit. So that's equal to the limit of the top divided by the limit of the bottom. And for a little bit of reasoning, we see this and this are both polynomials. What do we know about polynomial functions? They're continuous, so we know we can use our substitution theorem to evaluate this limit to just be the value at the function. And you can leave it as 2 over 8, or you could simplify it further. Now let's just take a brief look here. The difference between this and this, even though it's the same function, it was the point that we're at. In our first example, the point we were approaching was making the denominator 0, so we had to do more algebra before we could evaluate it. However, at the point 6, the point we were approaching did not make the denominator 0, so we could immediately evaluate it with our substitution theorem. Okay. Now, we don't have any limit laws for absolute value or cosine that we know of, although we could use the product rule for limits to split this up. But what we do know from earlier, even in our practice test, is that absolute value of x is continuous, cosine of x is continuous. We know from our list of information about continuous functions, the product of continuous functions is continuous. So x times cosine of x is continuous. That means we can use our substitution theorem for limits, which tells us the limit that's just equal to the value of the function. So evaluate pi for all the x values. Absolute value of pi is pi. Cosine of pi is -1. So our answer here is just -pi. Now, as we begin to think about this limit, we see we've got a fraction. So we know that we could split the limit into the limit of the top divided by the limit. So now we're looking at two separate limits. However, we know if we just evaluated this limit here, that would be 0, because tangent is sine over cosine, so sine of pi over 2 over cosine of pi over 2. Well, actually, it's not even 0, sorry, that's undefined, because that would give us something like 1 over 0, because sine of pi over 2 is 1, cosine of pi over 2 is 0. So the bottom limit is undefined, so we can't even evaluate this limit because it's not defined. When that occurs, our only hope for figuring out how to deal with this limit is actually through algebraic simplification. So instead of looking at this limit right now, let's leave it as it was, and instead think about how can we rewrite this. Now secant and tangent can be simplified in terms of sine and cosine. Secant is 1 over cosine theta. Tangent is sine theta over cosine theta. And we were finding this limit. So then we would get the limit, as theta goes to pi over 2, of dividing fractions. You would keep the first fraction, change the expression, flip the second fraction. And here we see that the cosines would cancel, particularly since we're inside a limit. And this limit simplifies to be okay. Now if I want to simplify this, I could look at the limit of the top, divide that by the limit of the bottom. Now the limit of the top is a known limit. It's the limit of a constant is the constant value. But for the denominator, we could say that this is continuous. It's one of our known continuous functions, which means we can use the substitution theorem. And we would get 1 over 1, because sine of theta of pi over 2 is 1. Now looking at our next limit, we would want to remember the two important trig limits that were mentioned in the notes. The one that is related to this is that the limit as x goes to 0 of 1 minus cosine of some input divided by exactly that input takes the value of 0. So this is page 29 of our course notes if you wanted to look at that. So we know the limit as some variable goes to 0 of 1 minus cosine of that variable divided by that variable is 0. So let's apply that to our problem. But we notice we don't exactly have that. For instance, the input to cosine of x is 4x, but we just have an x below. And also it's supposed to be 1 minus cosine of x, and we see we've got this constant multiplier of 2. Now the constant multiplier of 2 can be quickly dealt with because it's the same on both sides of the expression. You can factor out a 2, and you would be left with 1 minus cosine of 4x. All divided by x. So then we would get, you can pull the constant multiple out of the limit. All divided by x. Now this still needs to be dealt with. In order to use the rule, what's in the inside of the cosine has to be there below. So we really need there to be a 4 here. But I can't just write the 4 here because that would change the problem. So if I'm writing a 4 below the expression, I've got to counterbalance that with a 4 above. That way I'm really just multiplying by a fancy 1. Now this 4 is going to be drawn out of the limit as well, and we'll write that as 2 times 4, which is 8, times the limit as x goes to 0 of 1 minus cosine of 4x divided by 4x. Now this fits our exact limit law. So we know that becomes 0 because of this expression here. So we get 8 times 0, which is 0. Now one thing to note is, notice we modified the denominator by adding a scalar multiple. You could not get rid of the 4x inside the cosine because that's actually a composition of functions. It's one function inside another function, which we can't mess with, but we could apply this scalar multiple outside. Now in this example, we're asked this limit of this expression minus this expression over h is the derivative of what function? Well, if we know the limit as h goes to 0, the derivative is just this expression. So it's going to tell you what function it is if you just look at what you're subtracting. Notice we're subtracting this entire term, so it's the derivative of this function, and indeed we could verify. Notice we've got 2 times x plus h all to the 7th minus 3 times x plus h plus 1. That's exactly f of x plus h minus f of x. So this is representing the derivative for e. So this function, keyword is continuous on the interval from -2 to 1. Some values of the function are shown in the table below. We want the equation f of x equals 4.5 to at least have 2 solutions in the interval, and here we need to watch out. Notice it scales us to -1 and 1. So we're only looking here. It's as if we're just erasing that table because they said only -1 to 1. So mentally I would either scratch that out maybe or just think that it's not there. So let's just draw a quick sketch of what we see, and then it'll help us visualize what we need to do. We've got -1 is at 7. 0 we don't know where it is. That's k. It's yet to be defined. And then at 1 we have 5. Okay. And then what do we want? We want the function to cross the line 4.5 at least twice between -1 and 1. So what's happening is we would want our function to do something like go down and then up somehow. Now, the way we can know this is, since our function's continuous, by the intermediate value theorem, it couldn't come to 4.5, jump over, and then jump again. If the function's continuous and it has some point down here, then since it's a continuous function, it must go all the way through all values, so it hits 4.5 once there, and they would hit 4.5 once again. It cannot jump over the line. So by the intermediate value theorem, since our function is continuous and we have 2 points, if we can just show at 0 it has some value less than 4.5, we'll know that the function had to continuously pass through 4.5 on the way down and then on the way up. Looking at our options, this is not less than 4.5. For instance, if we were just equal to 4.5, then it could just hit it at one point and then go back up. That would be only one solution. So that's why that's not enough for us. Okay, 3 is below, 10 is above, 5 is above. There's only one option. 3 would have to be one of the values that would guarantee us at least 2 solutions. Okay. This is false. This is the wrong idea that you can cancel like that, which we can't because the 7x is inside the composition of functions. So that's false. However, 7 cosine of x over 7, notice now the x is by itself, the 7 is just a scalar multiple. That would cancel and just give you cosine of x, so don't confuse those. We know the limit as x goes to 5 is -2. Then do we know the limit as it goes to 5 from the right of the same function is -2? That's true. If you know the two-sided limit, you know both single-sided limits. F of x is a continuous function such that f of 3 equals 8, okay, and f of 15 equals 2. Then are we guaranteed that somewhere it has to equal 0 by the IVT? That would be false because remember, you're guaranteed by the IVT that you know it passes through all values on your endpoint. So if at 3 we're at 8, and then at 15 we're at 2. All we're guaranteed by the IVT is that it goes through these values. It might go through more, but we're not guaranteed that. For instance, IVT only tells you that it must pass through all values between 2 and 8. So that's false. Okay, this is asking us to find the limit, and this is from the right, from the left, and the two-sided. And we've got this piecewise function. So notice it acts like the line 7 minus 2x for all x values less than or equal to -1. And it acts like the function x squared plus 8 for all values greater than -1. And we're looking at the limits at -1. So at -1, previously our function is acting like some straight line with negative slope, and then after it's acting like the parabola. So as we approach through values to the left of -1, do you see we're approaching through values less than 1? So it'd be acting like this function. So the limit as we approach from the left is the same as the limit as x, oh, and that's for the left. That's what I was talking about, so I'm going to go here first. Is acting like this portion of the graph because we're approaching through values less than 1, so we're acting like 7x minus 2. Now we know that this is continuous, so we can use substitution. And we know the value of the limit is equal to the value of the function at that point because it's known to be continuous. So 9, that's the left-hand limit. Now as we approach from the right, we're approaching through values greater than -1, so we're acting like the parabola. That's why the limit as we approach from the right is the same as x squared plus 8, which again we know this is a polynomial, which we know is continuous. So we can use our substitution theorem, just showing our reasoning here. And we know it's going to be the same as -1 squared plus 8, which is 9. So the two-sided limit, if you know the right-sided limit at the point, the left-sided limit at the point, and they agree, then you automatically know the two-sided limit is 9. Because if the limit as x approaches -1 from the left of the function equals the limit as x approaches -1 from the right of the function, this tells you it's equal to the two-sided limit by definition. So the remaining portion is they ask us, is it continuous at x equals -1? Well, we know the function, the limit of the function exists. Let's evaluate the function at -1, and if it also equals if it equals 9, then it is continuous. So at -1, we are acting like this function because it said for all values less than or equal to -1. So f of -1 is evaluated in this function, and we get 9. So what we would say is, since f of -1 equals the limit as x approaches -1 of f of x, we know f of x is continuous at x equals -1. Great. Now in this next question, we're asked to sketch a graph of the function such that all the conditions are met. We first have to show a function that's continuous for everywhere from -4 to 4. It needs to be not differentiable at 1, but it needs to be differentiable at all other points. So let's mark our key points on the graph. -1, 2, 3, -4, 4, and 1. So we need to think about what are ideas of functions that are continuous everywhere, but not differentiable at a single point. And we know things that make the graph not differentiable. Those are corners or cusp, vertical tangent line, discontinuities, wild oscillations, things like that. But we can't have a discontinuity because it's supposed to be continuous everywhere. We can't have a vertical tangent line because that's a point of discontinuity as well. So we could do something that has a corner or cusp at 1. So for instance, something like this would work because it's continuous everywhere, but not differentiable at 1 because notice we don't have a unique tangent line at x equals 1 because of our corner or cusp. So just something like that would work. There's a lot of possible ways you could draw a graph that would fit these criteria. So that brings us to the end of our review. Remember, there are other review problems, but those were all covered during class. So if you want to look at them again, you could always reference our Zoom class recording on Canvas.